Okay, we're gonna cover state machines. So, state diagrams, counters, finite state machines, Moore versus Mealy state machines, and one-hot encoding and data path and control. So, what is a finite state machine? A finite state machine is like a machine that has states. What is a state? Is like, for instance, if I am, I'm the same person. I can be, dizzy, sleepy, happy, uh, awake, uh, energized. All these are states, but I am the same person. In fact, my person did not change. So this is the same thing. You have a circuit that has states, that goes through states, and these states, they're gonna determine the value of some outputs, and the state transition depends on the inputs. So this is what is the finite state machine model, as it is shown on the figure. So it uses combinational logic and storage elements. Storage elements are mainly used to store the state, the state, the state code. So every state has a different code, and then the code of the states is stored in the storage elements or memorization elements of flip-flops. Generally, they are using D flip-flops. All right. An example is synchronous counter design. Most requirements for synchronous counters can be met with available integrated circuits. In cases where special sequence is needed, you can apply a step-by-step design process. So what does it mean? It means like if we are trying to design a counter which sequence is not the usual sequence, so we need to do a specific design or a custom design. The steps in design are described in detail in the text and lab manual. So this is the lab manual of this. Of course, we are not going to do this lab. So start with the desired sequence and draw a state diagram and next state table. The gray code sequence for the text is illustrated. So this is the state diagram. So we go from 000 to 0001 and then 011. This is gray code. And then from 011 we go to 010. And then from 010 we go to 110. So you can see that only one bit is changing. From 110 we go to 111, and from 111, 101, and then to 100, and then back to 000. So here is the state transition table. So this is the present state and next state, and it's shown like that. And then we can see this is following the state diagram. So consider how many states and how many flip-flops use a K-map to derive the inputs of each flip-flop. The output of the K-map produces the combinational circuit for driving the next state. Try using D flip-flops, for instance, in this example. So the transition table again. So here, we can consider like every output variable, every next state Q as an output variable, and all the three input state variables from the present state to be inputs. And then we have like three kernel maps and three equations for the next state. Counters, they use simple finite state machines. This is a 3-bit up counter. This is a very simple 3-bit up counter. So we can describe that as a regular counter, or we can use a state machine to describe that. So counter design procedure: draw a state diagram, draw a state transition table, encode the next state functions, minimize the logic using K-maps, and implement the design. So it has no inputs. So here we have state diagrams, states, storage element, register values, a finite state. A finite set means a set that has a known number of elements. A known number of elements. or a bounded number of elements, something that is fixed number of elements. Transitions, changes from a state to a state, not in a state. So changes in state or from a state to another state. So usually synchronized by clock. It's not usually, it's like 99.9% of the time. So FSM sequence through states. So based on inputs and present state. So if we are in a state, let's say we are in 0, 1, 0, and then we go right away to 1, 1, 1, 1 without any input requirement. But if we are in 1, 1, 0, we have two outputs. So we go to 0, 1, 0 if the input is equal to 0, and we go to 1, 0, 0 if the input is equal to 1. So input is determining the transition to which state we are transitioning. Robust design. What if our design starts in a 1, 1, 1 state? So we have, this is a counter. So we go to from 0, 0, 0, 1, 1, 0. From 0, 0, 0 to 0, 1, 0, and then to 0, 1, 1, and then to 1, 0, 1, and then to 1, 1, 0, and back to 0, 0. We have a set of red states here that are invalid states, but what if our counter starts in one of these invalid states? So we will get stuck. We'll never come back to one of the legal states. So that's why we must design the counter to escape invalid states, and this is how it is done. So this is one way of doing it. So we are starting designing it so that even there is no chance that we are going to go to any one of the invalid states, as you can see in the second diagram, but we can always go from an invalid state to a valid state. So this is the most important part. Self-starting counters ensure that invalid states transition to valid states. Okay. Startup and bit error tolerance may limit our ability to exploit don't cares. Choose startup transitions that minimize the logic. So how are we doing it? This slide is describing how we can do it. So this is one way of doing it. So for instance, if the present state is 0, 0, 0, 1, and next state should be chosen as 1, 1, 0. So we chose arbitrarily. And here, if we are in a state that is illegal, which is 1, 0, 0, 0, we are choosing 0, 1, 0. So choosing which state we go to is something that is based on the ability to exploit the don't cares, the ability to see, it's a custom thing. It's per design basis, on a design per design basis. Moore versus Mealy machine. A Moore machine or a Moore type finite state machine is a machine where the outputs depends only on the state, and the next state depends on the inputs, right? In a Mealy state machine, actually, the outputs depend on the current state and the inputs, while the next state depends on the current state and the inputs, same way as in Moore. But the outputs depend also on the inputs, which is a Mealy machine. This is a YouTube video link that I invite you to watch about Moore and Mealy machines. So it's very useful to watch. So I'm not going to include it in this video, but you can watch it on your own. So specifying outputs for a Moore machine. So that's the idea. In a Moore machine, the outputs are specified within the state. So you have the circle here. You can see a circle A. This is state A /0, means the output is 0 here. Because the outputs depends on the states, so the outputs are coded inside the state. So this is the output. So next state A, B, C, like current. These are literals that are coding states. So states will have numbers, but uh, we, 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 we have a number of bits to represent the states we're using flip-flops, but here we're just using symbols of states or labels, names. Name A, state B, state C, state D, and E. That's it. And then the value of the output here, you can see 0, 1, 1, 0, and 0. And of course, the transition is governed by the input value. So here, to give you an example, if we are in state A, then the output is 0, and then we move. If the input is 0, we go to state B. If the input is 1, we go to state C. And in both cases, the output is going to be 0 as well. But if we are in state C, for instance, if the input is 0, we go to state E, and then the output becomes 1. And if the input is 1, we remain in state C, and the output is still 0 as well. How about for mini machine, the outputs are specified based on the inputs, because the transition, what is a mini machine? Mini machine is, there is a transition between current state and next state. So this is transition. And it depends. So it depends on the current state, and it depends on the input. So because the value of input is determining what is the next state, then we know the value of the output. So that's why the output here is specified on the transition arrow rather than inside the state circle. Okay? All right. So this is a detector for 0, 1, or 1, 0. More versus mini machines. More machines are safer to use. Outputs change at clock edge, always one clock later, may need more logic to decode state into outputs. Mini machines usually have less states, so because the outputs, they require less transitions to achieve a given condition. So react faster to inputs, don't need to wait for a clock to issue an output when the input that is driving that output is being fired. So asynchronous outputs and asynchronous feedback are dangerous. So this is another thing, because if your logic is going to be very late, then you don't have a lot of time to transmit your result across to the next flip-flop. All right, following our set of quizzes, I'm not going to cover that. You do that on your own, or we can do that in class. Okay? Thank you very much.